be given by Dr. Chuck Garland, please.
Thank you, Michael. Am I on? Yes. Okay, so sorry about that. So I've been asked by the organizers to give an overview of the Oseen-Frank model. And I also thought I was going to be able to slip in some additional observations that were kind of pertinent to the workshop, but it didn't seem to work. So my apologies, just the first half of what is discussed in my abstract. I think I should have used the to-be-announced device. But at any rate, I'm happy to talk about the Oseen-Frank. I apologize to the many people in the audience who will know this already, especially those who will know it better than I do. But let's give it a go. I'm grateful to the Institute and to the organizers of this program and to the organizers of this workshop for the opportunity to speak here. So the Oseen-Frank model has already been mentioned on various of the talks from yesterday. So there's a little bit of redundancy, but not too much, I hope. The background, it's a macroscopic continuum model for the equilibrium orientational properties of a system in a liquid crystal phase. It's variational in nature. It's built by phenomenological procedure where a set of rules are laid down and essentially all the independent terms that follow those rules are included. Constants or parameters are put in front of those terms, and the hope is that they can be measured and used to model experiments and devices and things. It's a model that pertains to the nematic liquid crystal mesophase. So this is the simplest liquid crystal order as discussed yesterday. So there's orientational order, but no positional order. There are essentially two flavors of the model, just one which is normally referred to as the nematic version, which just applies to an ordinary nematic, sort of your standard rod-like molecules. And then there's a version of the model for chiral nematic or a cholesteric, which differs slightly and has a ground state with an inherent tendency to twist rather than maintain a local parallel alignment. The model assumes a uniform degree of order, so there's no scalar order parameter. The order is assumed to be of a constant value throughout the sample. Temperature is taken to be a constant, as is the mass density. And then the key variable, state variable that describes the orientational state of the system is this unit vector field n hat, which is known as the director, which can be thought of as the average orientation of the distinguished axis of the molecular architecture in a fluid element at a point. Or you can think of it as this Q tensor was mentioned in various talks yesterday. It's the distinguished eigenvector of a uniaxial Q tensor. So the whole model, this is the sort of the dependent variable in the model. The model has the generic form of an integral functional, usually denoted by f of this director field n. And in its simplest form, the equilibrium state, the globally stable equilibrium state, is the director field that minimizes this integral functional over some set of admissible director fields, which includes regularity conditions, boundary conditions, and the unit length constraint. The integral functional is constructed by integrating over the volume containing the liquid crystal sample of a density function, which is referred to as the distortional elastic energy density. It is assumed to depend only on n and its first order gradients. Essentially, and then this is where all the modeling basically goes in, what to put into this density. And the role of this density is to somehow just penalize the director field for departing from the preferred state of orientation. And so in the simplest, in the uniaxial and the nematic version of the model, the preferred state of orientation is just local parallel alignment of the directors. And as was discussed yesterday, this arises through intermolecular forces of either steric nature or weak van der Waals kinds of interactions. In most modeling situations utilizing the Oseen-Frank model, There will be additional terms besides this distortional elasticity present, and the most common versions you could have either magnetic or electric fields or both, surface anchoring potential, as was discussed a lot in Oleg Lavrentovich's talk yesterday. And sometimes there are additional terms related to the flexoelectric polarization. And I'll try to touch on each of these terms and show what is added. So it's a phenomenological model, and so you have to lay down a set of rules to build it with, and essentially the rules are these. It's a continuum model, so the underlying assumption behind all of this is that the variations of your director field are slow on a molecular length scale. The frame indifference is an assumption that must underlie any physical model, and in this case, this was also appeared in various talks yesterday. The frame indifference assumption is essentially that the free energy density or the distortional energy density should be unchanged under any proper rotation, proper orthogonal transformation of your coordinate system. And then there's an addition, a slight variant of this in Epifanio's book. This is referred to as material symmetry. There are these two different flavors of the model, and for the nematic version, it is additionally required that the symmetry this symmetry group include reflections, because the purely nematic phase should be invariant. The energy should be invariant under reflections as well. The cholesteric version is different, however. The cholesteric just needs to obey this invariance property because the reflections take a right-handed cholesteric into a left-handed cholesteric. It's a different system, and in principle it could have a different energy. The invariance of plus minus n has been mentioned several times in terms of the phenomenological modeling assumptions here. That means that the density must obey this for all admissible director fields. The assumption is that you can truncate this at terms that are quadratic in this gradient, and so the basic model doesn't include any higher order powers. It doesn't include any higher order gradients, although there will be at least a couple of other talks concerned with this K13 term, which when you assume this, it's not allowed, but as was classically done. But there are arguments that you can make that there's another term that should be included, but it's outside the realm of this assumption. The energy density is assumed to be non-negative, and you usually take advantage of the fact that you can kind of normalize things so that it is exactly zero on what you're taking to be your ground state. So once you lay down these assumptions and examine all the possible independent terms that you can construct that obey those rules, you come up with essentially four terms. They can be combined and written in various ways, and so there are different ways you will find these in the literature, but there are, at least for the first three, this is kind of the standard way that people have taken these. So you get sort of four independent terms that are quadratic in the gradients and obey all those assumptions. And in front of them, you put these constants, which are, again, another convention. Sometimes this constant is referred to in this way as a combination of K2 plus a new constant K4. Sometimes this constant is referred to as K sub 24. Either way, these are the four terms that are going to the basic uniaxial or the basic nematic version of the model. The elastic constants, so these K's are the Frank elastic constants. They've appeared in several talks yesterday already. They depend on temperature generally, for a particular investigation or for particular modeling of this. You would generally be doing this at a constant temperature, but if you look these constants up, you will see them quoted at 26 degrees Celsius or whatever. The non-negative assumption implies that the K1, 2, 3 constants must be greater than or equal to 0. The K2, 4 combination must satisfy this inequality. So K4 in principle can be positive or negative, but it just can't be too negative or too positive. And okay, so with that, this is set up such that the sort of ground state, the preferred state, the state that gives you the least possible value of this density, is the state in which the director field is constant, uniform in space. So the director is just a constant, you know, it can be oriented in any direction, but it's just a constant uniform alignment all through space. If you take the director to be constant, it'll have, these are all just, they all involve differential operations on n hat. So the divergence will be 0, the curl will be 0, and the density will be exactly 0. And since it's greater than or equal to 0 by construction, that you can't get any smaller than that. The surface term, well, this last term, this fourth term in the density is usually written in a way that's more convenient for some of the calculus. There are various ways you can turn these terms around in different kind of sign conventions, but essentially this term, the trace of grad n squared minus the divergence of n squared, is a pure divergence itself of an expression that looks like this: curl n cross n minus divergence n times n. So as such, it can be integrated by parts to the boundary confining the liquid crystal. And if you have sort of a strong, what physicists what would be called a strong anchoring condition on the boundary, which means you have a Dirichlet boundary condition on the n hat director field, this just contributes a constant to the free energy, which wouldn't affect the equilibrium states. And so this term, you know, and often this term is also forced to be 0 by just the kind of symmetry of the system, the geometry of the system. So this was, I think, when Ian was giving his talk yesterday, he mentioned this as because of this. This is a null Lagrangian. When you write down the equilibrium equations in their strong form, this term, there's no trace of this K4 constant around anywhere. There is a simplified version of this model that's frequently appears and is useful for sort of simple, sort of idealized explorations. I mean, to model a real system or a real device, you need to use the measured versions of the elastic constants. But to get the qualitative picture right, you can frequently work with the so-called equal elastic constant model, in which K1, 2, 3 are assumed to be equal to the same constant. K4 is taken to be 0. In that case, combining all these terms and doing the appropriate simplifications, the density just collapses to the grad of n squared, or in components, it's just the sum of squares of all the first partials of all the components of the director field. The cholesteric model differs from this slightly in a couple of ways. So here, this term highlighted in red, there is a new term that is allowed in the cholesteric model. This is a scalar. This is the sort of a wave number for the helical twisting state that forms the ground state. So in the other model, this term was not present there. The Q naught was essentially 0. Also, you can take advantage of this normalization and kind of figure out that you can take the K2 plus K4 term to be 0 in this case as well. This is talked through in Ian's book pretty well. So the inequalities, which I forgot to mention before, those inequalities I think were first derived by Jerry Erickson. They're usually referred to as Erickson's inequalities. Here, the necessary inequalities that the K's must obey are they just must be bigger than or equal to 0. This Q naught can be positive or negative. If it's positive, you have a right-handed helical ground state. If it's negative, you have a left-handed helical ground state. And then a length scale is, so the cholesteric pitch is 2 pi over the magnitude of Q naught. And I guess I should get the ground state down here to see this, what this means. This is essentially the sort of spatial period over which this twisting ground state undergoes a full rotation of the director. So here, the state that gives you the least possible value of this energy density is no longer a constant uniform director field. It is a director field that takes a form like this, cosine of this Q naught, the same Q naught from there, times z in the x direction, sine Q naught z in the y direction. So if z is the upwards direction in my coordinate system, it's just a twisting state of the director. Right-handed if Q naught is positive, left-handed if Q naught is negative. And if you take such a director field, its divergence is 0, its curl is parallel to the director field with a factor of minus Q naught. And so all these terms wind up going to 0 as a result, and you get the energy density evaluates to exactly 0 on this state. So the model, so in minimizing the free energy, the state that is encouraged by this model is some kind of a helical twisting state with a prescribed spatial period, the cholesteric pitch, but it's degenerate in space. It can be doing this, the helical axis can be going in any direction in space. Now, I was disappointed that I couldn't find better pictures in my files of these things, but this is the standard interpretation that one attaches to the terms that appear in the energy in the distortional energy density, and there are nicknames associated with the 3 elastic constants, and so if we I think we know what the terms look like. So if you construct, for example, if you construct a director field that is a splay type field, the field of a point source, just a director field emanating from the origin in a radial direction, then you will find that it has a 0 curl, so there is no contribution from the twist term or the bend term. It has a splay, which is like 1 over r, or 2 over r, depending on 2 or 3 dimensions, I guess. And so you just get contribution from the K1 term. So this field would look something like that, either in a cylindrical symmetry or in a section of a spherical symmetry. Similarly, you can construct a field which exposes the K2 term, but which is 0 on both the divergence and the n cross curl n terms, and it's just this helical rotating field here. And finally, the bend term would correspond in a cylindrical coordinate system to a director field that just goes like the p hat theta unit vector. So each one of these terms just exposes one of the elastic constants, and this is why they have acquired these nicknames. The K2-4 term, unfortunately, I don't believe that there is a simple analytical field that you can write down that will be 0 for K1, 2, 3, but will expose just the terms in the K2-4. I mean, you can do it via a limiting argument. Epifanio has this in his book. It's nicknamed the saddle splay constant because of the kind of limiting distortion that you have to construct. But people can correct me if I'm wrong, but I don't think there's such a simple formula here that you can write down, which will be have a non-zero K2-4 and be 0 in the K1, 2, 3 terms. So I didn't try to reconstruct that. So you could tell, I think, from Oleg's talk yesterday how important things like length scales are, and intrinsic length scales in this kind of modeling area. And so this model is particularly simple in this regard. F is an energy. The distortional elasticity is energy per unit volume. So the constants have to be of the dimensions of energy per unit length, or a force. So you frequently we'll see them quoted either in newtons or piconewtons or joules per meter or something like that. And then Q naught, if you have the cholesteric version of the model, the Q naught is different from 0. It's like a wave number, so its dimensions are 1 over length. I dug up typical values. I just pulled these out of the appendix of Ian's book. This was already mentioned in Oleg's talk yesterday. These are the values for a kind of a typical low molecular weight liquid crystal as you might have in a display device. 5 CB is the nickname of the material. These were the measured values at 26 degrees Celsius. And so here are the experimentally measured values of K1, K2, K3 for this material at this point, at this temperature. And as Oleg indicated yesterday, the order of magnitude of these elastic constants is of the order of tens of piconewtons, which is what this basically is. 10 to the minus 12 newtons is the piconewton, so you frequently see these things quoted like that. The other sort of rule of thumbs that you usually have associated with these kinds of low molecular weight materials are frequently the K1 and K3 constants are sort of comparable in magnitude. The K2 constant, the twist constant, is generally a little bit smaller, frequently roughly of the order of half the magnitude of the K1 and K3. Now, in terms of length scales, if you all the Ks have the same dimensions. I mean, you cannot create any intrinsic length scales out of the Ks. You can form dimensionless ratios, and they're sometimes they're frequently important, but you don't get length scales out of that. The way length scales are introduced into the model is if you have the cholesteric pitch, then that's a length scale in itself. If you have a surface anchoring potential, then you get a boundary extrapolation length, as Oleg utilized in his comparisons yesterday. And if you have magnetic field or an electric field, you can identify certain length scales associated with the magnitude of those fields. But otherwise, this is sort of a truly macroscopic model. Just without these additional features, you do not have you do not have intrinsic length scales, which in a way it distinguishes it, in my view, from the Landau-de Gennes model, where you have distortional terms, bulk terms, the ABC coefficients, and they have different dimensions, and from them you can form intrinsic length scales which are of molecular order. So that's usually referred to as a mesoscopic model, where this is a macroscopic model. Electric fields are frequently used to control or orient liquid crystals, as has been discussed. In a typical situation, you will have a liquid crystal sample sandwiched between some electrodes that are connected to a battery or a power supply. And so you're in the realm of sort of a capacitor held at constant voltage. And then these are the relevant electrostatic variables. The electric field can be taken to be the negative gradient of electrostatic potential. The electric displacement is related to the electric field in this way, and also involves the induced induced polarization. And these materials are anisotropic. They're usually more polarizable along one direction than along transverse directions. So the relationship between the induced polarization and the electric field is a tensorial relationship. And if you combine these, you end up with the displacement having the electric flux having a tensorial relationship to the electric field. This tensor is known as the dielectric tensor, and it depends upon the local orientation of the pneumatic director. In the frame of the director, or in a frame in which the director is sort of the third frame vector, you just have it's a uniaxial symmetry. So you just have two relative permittivities, usually referred to as epsilon perp, a relative permittivity usually referred to as epsilon parallel, and this can more concisely and cleanly be written in a tensorial notation like this. The difference between epsilon parallel and epsilon perp is the dielectric anisotropy. It can be positive or negative, although the constants themselves are all strictly positive. The electrostatics then, the electric field in a static equilibrium situation must obey the standard electrostatic equation. With no charges present, no charge density, the divergence of the electric flux of the displacement must be 0. And so in that case, this becomes a second order PDE for the electric potential. And so liquid crystals are anisotropic, and so this is, if in the simpler case of an isotropic homogeneous medium, this would just be Laplace's equation, which is the potential equation by definition. And so this is just, it's a nice enough equation. It's just epsilon ij is positive definite, a real symmetric tensor field. So it's just an anisotropic inhomogeneous version of a Laplacian type, Laplace type equation. The director field does have an influence on the electric field, and the electric field has an influence on the director field. It's a coupled interaction. If you take the electrostatic equation and break it out into pieces, you will have a piece out front that is independent of the director field, just a Laplacian on the electric potential. And then the director field part takes this form with a ratio of the epsilon A over epsilon perp in front of it. And this is the term through which the director field can influence the electric potential. In general, this constant is order 1. And so this is, depending on what the director field is doing, this is a sort of a non-negligible effect. The electric field will definitely be altered or affected in a noticeable way by the presence of the director field. So when an electric field is present, you must include an additional piece in the energy density associated with it. The piece comes in as minus one half the energy density stored in the electric field, and if you just use replace the electric field by the negative gradient of the potential and simplify it, you can break it off into sort of two pieces in the energy. A piece which does not have any coupling between n hat and u, and a piece that does have a coupling which has the multiplicative factor of epsilon A in front of it. So you can regard this now as an integral functional for two independent fields, the director field and the electric potential. And the first variation, the vanishing of the first variation of this functional simply produces for you your electrostatic equation. So you still have a nice variational formulation of things. The only thing that's a little funny about it is that whereas the globally stable equilibrium states minimize the free energy with respect to the director distortions, because the electric field enters in this negative coupling way, it actually maximizes the equilibrium electric field is such that it actually maximizes over the electric potential. So it has sort of an intrinsic minimax field to it, or since the electric field part can be easily sort of extracted for any given director field, you can uniquely solve for the electric field. You can think of this as a pure minimization problem subject to a PDE side constraint, and that is frequently convenient to do. The other reason I wrote this out in detail is that you can kind of see the different influence of this term. When epsilon A is positive, since the director is seeking to minimize this expression, n is encouraged to align parallel to the electric field. Sorry. And when epsilon A is negative, just the opposite effect is manifested by this term here. N is encouraged to align perpendicular to the local electric field. So you get a completely different coupling and influence. The inclusion of a magnetic field is very similar, but there's one key difference. The modifications of the free energy is similar. You must include a term related to the magnetic energy density The magnetostatic relationships are very similar to the electrostatic relationships, and I've written them out there, but in this case, these materials are such that now here I have a question. That wasn't the materials. The diamagnetic susceptibilities or permeabilities or whatever are such that the magnetization, the induced magnetization, is so small that the magnetic field can be regarded as uniform or kind of unaffected locally by the liquid crystal, as opposed to in the electric field case where there's definite coupling. Now, if I look in the textbooks for the justification for this, I can find quoted values of just chi A, chi parallel minus chi perp, and people say chi A is of the order of 10 to the minus 6, so we can take H to be constant. But it seems to me if you write down the magnetostatics equation that is the analogous to the electrostatics equation, the relevant ratio should be chi parallel should be chi A over chi perp, because that's the coupling between sort of the Laplacian term and the perturbative term. So I don't know. I would be appreciated if one of the physicists would at the coffee break explain this to me. But I'm a little bit confused about this issue myself. So typically, since part of this contribution is just it doesn't involve a coupling, just adds a constant to the free energy. When there's a magnetic field present, what people frequently do is just adopt a simple form like this. You just add a coupling term here, and the magnetic field will have an aligning effect when chi A is positive, or a misaligning effect when chi A is negative, and now you just get simply a pure minimization problem. H can be treated as a load or an imposed force or torque, and you don't have to worry about the minimax complexities. Here's an intrinsic length scale that you can construct out of the new parameters that appear in the density when you include the magnetic field contributions, and frequently some of the effects and the interplay of the different terms in the model are expressed in terms of ratios of this magnetic coherence length to geometric length scales that might be present in your model. So electric fields, magnetic fields, the other types of terms that you will sometimes see included in this kind of modeling are so-called flexoelectric terms. This has to do with some electric field effects that can be induced strictly by the distortion of the director field. And this is attributed to Bob Meyer from 1969 PRL, but the symmetries are such that, depending on the particular materials, the presence of a distortion of this form, a divergence, the presence of a curl or a bend type distortion can possibly induce a local polarization. And then this could couple to an electric field, or it could even lead to the development locally of an electric field. E1 and E3 are known as the flexoelectric coefficients. You see them with different sign conventions. This is the sign convention that's in Sven Lagerwald's book. And then if this effect, it must be included. There is a term that you must add. The polarization will couple to whatever local electric field is present by the addition of a term of the form minus P dotted with the local electric field. The electrostatics are still the same. You just have added, in addition to the induced polarization, in principle, you have an added flexoelectric polarization. So if the flexoelectric polarization, if this distortion is not divergence free, it can lead to the creation or alteration locally of the electric field. Those are the two types of fields that can be included. Flexoelectric terms can sometimes be included, and then The last thing that you will sometimes see in this model are additional terms to account for a weak tendency of the confining substrate to encourage a particular alignment of the director. So frequently in the modeling, you will see the distinction made between a so-called weak anchoring and a strong anchoring. Strong anchoring, just in mathematicians' terms, just means you have a Dirichlet boundary condition on the director field on all or some portion of the confining boundary. Weak anchoring means the confining substrates or whatever were treated in such a way as to encourage a type of alignment, but not hold it perfectly well. There are various versions of this. Oleg discussed the role of these surface terms quite a lot. Usually they just depend on the unit normal to the boundary at that point and the director field. And they can either be, encouraging alignment in a certain direction or discouraging alignment from a certain direction. And these enter the question, yeah? Yes, for free boundaries, if a portion of your boundary is free, you would just have this being 0 on that, and there would be a piece of the natural boundary. So normally, if you write down the natural boundary conditions, you'll get a piece that comes from integration by parts of the distortional elasticity to the boundary, and you get a piece from W surf. And so if the boundary is free, there's no W surf part. Kind of be the distinction between a pure Neumann boundary condition and a mixed Robin type boundary condition.
There's surface tension effects.
Well, this isn't quite the same as surface tension, I don't think.
Free boundary is a strong anchoring agent.
I'm sorry?
The free boundary nevertheless would give you strong anchoring, typically perpendicular.
Yeah, but it also kind of depends. I mean, if you have an equal elastic constant case with a free boundary, it just collapses to normal derivative is equal to 0. Jonathan, you're trying to say something.
And I think that there's a difference between what mathematicians would call a free boundary versus what physicists would call a free boundary. Right? For mathematicians, a free boundary means a boundary with no preference for the orientation in one direction or another, right? For physicists, a free boundary means the edge of the liquid crystal next to air or vacuum, right? Which would probably have some preference for the orientation.
That's what I mean.
Yeah, okay.
In fact, a very strong one.
Which would have a very strong preference, right? So what you had in mind is different from what Chuck was thinking of.
But there are boundaries that don't care, but they're hard to make.
Any interfacial
the first
boundary
type we
imposes
would
an
call degenerate
enormously strong
Yes.
restriction.
I guess what I meant free in the sense of not a priori prescribed. You have to solve for the boundary too.
Right, and all, whether you have
Yeah.
right, that's definitely
Yeah,
the case.
there's that too.
Okay, well, I'm running out of time, and I've got 40 more slides to go. Some typical values. This is the surface extrapolation length that Oleg found very important in discussing the colloidal modeling that he's been involved with. I need to move quickly here. I'm running out of time. I had the equilibrium equations associated with this model can be written in a lot of different ways, and they have a generic form. If you have no electric field and you're forced to model everything in terms of director components, the first variation generically has a certain form. And then the weak forms of the equilibrium equations are these sort of variational statements of the vanishing of the first variation either on the tangent space to the director field at the point, or if you do not restrict the variations and allow them to be general, then you need to introduce Lagrange multipliers both in the bulk and on the boundary to enforce the pointwise unit vector constraint. In strong form, here's the sort of weak boundary condition that we were kind of just discussing. When the boundary is sort of completely degenerate or free, this term would be 0, but you would still have this normal derivative kind of term. I better quickly get to the summarization. Writing down characterizing stability of an equilibrium solution is a little complicated. You need the Lagrange multipliers from the equilibrium equations. And frequently, when people work with this model, they try to avoid having to deal with the director components and the Lagrange multipliers. And frequently, it's the systems and the solutions are simple enough. You can represent the director in terms of orientation angles. And in this case, the pointwise unit vector constraint is taken care of automatically, and so you don't have to worry about that aspect. I don't have time for my example. I was going to try to give an example that illustrates this, but when you use an orientational representation, everything is changed to coupled equations, in this case a 1D example, coupled equations in terms of the orientation angles. And even in a 1D case, you can have rather complicated behavior to analyze, but I don't have the time to go through this. So let me summarize. I think the Oseen-Frank model, I think people would generally regard it as very effective for modeling a lot of problems at the device or experimental scale. As Ian discussed yesterday, it's consistent with Erickson-Leslie hydrostatics, provided a certain compatibility exists in the body forces that appear in the linear momentum equation. It admits point defects in the sense that a pure splay distortion, which is a singular vector field, still has a finite energy in this model, but it does not admit line defects in the sense if you have a cylindrical line defect, this has a divergent free energy. There are notorious sort of parity issues in the sense that while minus n and plus n are by construction equivalent, you take any director field and you will get exactly the same value of your energy functional if you take minus it everywhere, but you can still have problems locally. That didn't come out well enough, but this is kind of like a half-strength disclination line, but essentially you can get situations locally where your n hat is pointing one direction and very nearby is pointing another direction. So there are I didn't put this in here. There are kind of workarounds that people have to deal with things where they anticipate such a problem being present. There are workarounds where you can try to rewrite the energy density in terms of tensorial representations, but still at fixed degree of order. I would say if you work with this model, this pointwise unit vector constraint can be a real nuisance. Oh, I forgot to mention here, this parity issue was looked at by John and R. Gear. They developed some ideas for when you could guarantee, depending on boundary conditions and the geometry of your boundary, when you could guarantee that your field your equilibrium field would not encounter this. The math analysis was done by Hart, Kinderlehrer, and Lin for the basic existence and regularity results. Most of the stuff I've talked about has been textbook stuff. I generally took it from Epifanio and Ian's book. So thank you very much. I'm sorry for running over a bit.
Okay, thank you very much for your talk. Unfortunately, we do not have time for questions, so we will leave the intriguing topic about whether direct